This is a video solution of the practical session on cold thermal power plants that we did last week. This exercise talks about the thermoelectrical power plant that has an electrical nominal power of 160 megawatts, and it burns black lignite. You can see the composition here, and you will use this information later. What's important for us now is to see first how the power plant works. We know that the efficiency of the boiler is 92%. So when we will burn coal, only 92% of this heat that we obtain will be transferred to the cycle effectively. Here we have the conditions of the points, and you can see that we have three pressure levels: 180 bar, 45 and 0.058. This will be the condenser, and we have two turbines, the high pressure turbine and the low medium turbine. We get some of the points, 1, 3 and W, we get the real points, but for 20 and 4, 2 and 4 we get only the ideal point. Let's try to see, let's see first how this power plant is. So here we are burning the lignite, so we are transferring heat to the cycle here at the boiler. Let's start by drawing first the diagram, the TS diagram. This will reveal the most important information for us to make the following calculation. So it's very important to do it accurately and to know to do this step. We always start by drawing the bell that separates the liquid plus the steam from the steam. So here we have liquid, here we have liquid plus steam, a combination, two-phase flow, and here we only have steam. So let's first draw some pressure lines. This is the second step that we need to do. In this case we have three pressure lines. One is at the condenser, so it will be here with a very low pressure. I think pressure was 0.058 bar, so this is really low pressure. And then we have two more pressure lines. One, I first draw here where it should be located approximately, so this will be the 45 bar line, and this will be the 180 bar. We complete it by doing some additional, the continuation of the line, and here in the liquid it goes pretty close to the bell for both pressures. So let's start now the cycle. I like to start the cycle always from the exit of the condenser. So because the condenser is a big tank which has a mixture of steam and liquid, but all the liquid, saturated liquid, is gathered at the bottom, and this is where our pump is connected. So pump is getting water from the bottom of the tank, so it's liquid water. So this is the point before the pump, and now we pump the water. We pump at which pressure? You can see here that we are going to the high pressure turbine first, so we are pumping at 180 bar. So we pump here, and this is our point W, okay, the exit of the pump. Now we come here and we are moving through the boiler, so we are actually heating up to 530 degrees. This is pretty high pressure, pretty high temperature, so we know it's a slightly above the bell even. So it has to be superheated steam somewhere here. Okay, so that's now our point number 1. And here we decompress. We don't go straight down, but the real process has some going forward. So up to point number 2, which is in the isobaric line of the 45 bars. So this will be our point number 2, real. Now the ideal point would be with the not an increase of entropy, so it has to be somewhere here. Okay. Now from point number 2, the real one, we move again through the boiler. So we heat. If we heat, we are increasing in temperature, but we keep the same pressure. So we move in this line. And we reach the same temperature here as number 1, but now we are in point number 3. Now, at point number 3, we decompress until we reach the condenser, point number 4. And now we condensate more and more and more steam, so we are reaching the saturated liquid. Okay, now you know that here we have all this process of condensation, and there is very important aspect here to take into account, which is the quality. The quality here, the quality is the amount of steam present compared to the total, so the mass of the steam compared to the total mass in a certain volume. So in the small regions at the top of the condenser, you have a certain amount of steam, big amount of steam. So X will be close to 1. If we would move here at the bell, we know that here the quantity of steam over the total quantity of mass is 100%, so quality is 1. Here everything is liquid, saturated liquid, so there is no steam, quality is 0. Okay, in between we have a certain value, we don't know. Okay, so that's our TS diagram. So, and then it says calculate the real points, 1, 2, 3, 4. Okay, 1 and 3, they are already calculated. Okay, point number 1, we are only going to calculate the enthalpies. We know point number 1 and point number 3. Let's get the points number 2 and 40. It's good that we have the efficiency, internal efficiencies of the two turbines. So, and we are going to use that because the internal efficiency of the turbine, high pressure turbine, is the comparisons of these two processes. So this is 2 ideal and this is the number 2 real. So the efficiency here is what we really obtain divided by what we could really obtain if the process was perfect, ideal. So the perfect process is H1 minus H2, 0, ideal, no? As written in the handout. But we don't obtain that. We obtain H1 minus the real point. So here you can see that we know H1, we know H2, and we also know the enthalpy. So we can get that H2 is equal 3039 kilojoules per kilo. Okay, the same is true here. This is H4 ideal and this is the real one. Alright, and we do the same. The efficiency on the low pressure turbine is equal, now is H3 minus H4, H3, the ideal process, H40. And the same again, we know H3 and we know H40, so, and the efficiency, so we can easily calculate from here that the real point is 2346.4 kilojoules per kilo. Okay, so that's it for question number A. We get all the points 1, 2, 3, 4, and we can move to question B. Determine the thermal efficiency of the steam real cycle. Now, it's very good that we have already all these points, because now this question will be quite easy for us. The efficiency of the cycle will be the work that we obtain, the net work, divided by the heat that we are putting. Okay. No, so the heat that we are adding, we are putting heat in all this part here and here as well. So heat added will be the mass flow of the steam multiplied by, first, the difference of enthalpy from 1 to W, H1 minus HW, plus the heat added here from 3 to 2, H3 minus H2. Okay, what is the work that we obtain? The work that we obtain is the work here, the low pressure turbine, and the work here, high pressure. Okay, so again the mass flow, and now we need to multiply the difference of enthalpy from 1 to 2 and from 3 to 4. So H1 minus H2 plus H3 minus H4. Okay, and the result is 0.405. Now we could consider also the pump, because we need to put some work here for the pump, but the work at the pump is really low, and in this type of exercise for water, when we pump only water, the work required is very little. Okay, so that's it for question number B. Let's move to question number C. It asks us to determine the total efficiency. The total efficiency, this is the cycle efficiency. Total efficiency will be the efficiency of the cycle multiplied by the efficiency of the generator, mechanical generator, but also we need to multiply by the efficiency of the boiler that we saw at the beginning, because not everything that we burn, not all the energy from the burning goes to the cycle. So actually here we need to put the boiler efficiency, and that's our total efficiency, 0.36. It also asks for the heat rate. We know that the heat rate represents how much energy we need to put to obtain 1 kilowatt hour. So how much energy we need to put to obtain 1 kilowatt hour. That's the opposite of the efficiency, so we can already write that this is the opposite of the total efficiency. But heat rate is usually expressed in units of kilocalories divided by kilowatt hour, so we need to multiply this number by 1 kilocalorie is equivalent to 0.00163 kilowatt hour. It can also be 860 kilocalories is 1 kilowatt hour. It's the same, and we obtain 2379 kilocalories per kilowatt hour. Okay, that will be the solution for this section. Let's move now to option number D, which is rather simple. Let me keep this on top because we need it. Option number D, it's only asking what percentage of improvement from calculations B represents having regenerative steam extraction, because they are telling us that the heat rate is not really 2379 as I just calculated by 2250. Okay, so the real heat rate is equal to 250. So from here we can calculate what is the real efficiency total, because this is the opposite of the heat rate with the change of units that we did before. Okay, so now this is the total new or real. Now the improvement is the new efficiency divided by the efficiency old, and this will give us 5.7%. Okay, we can do it also directly from the heat rate, but you have to be careful when you do that, because you need to have the old heat rate above and the new heat rate below. Okay, of course this is -1. This is 105.7, so the improvement is 5.7%. Okay, question E. Question E asks, what is the amount of steam? So now from the total actual heat rate you should find. So now we know that it's not exactly the same, and the difference is that there are regenerative heating of the feed water. And then it asks, what is the amount of steam produced in the boiler? So we need to calculate the mass flow that's going through the boiler. We don't know that. Considering that in reality point W actually has an enthalpy of, so we had that point number W was 121 kilojoules per kilo, but it says that it's not that value. The real point is much more, 1002 kilojoules per Kelvin, per kilo. So and this is due because there is one extraction of steam of 15 kilos per second at the outlet of the high pressure turbine. So here not all mass flow will go through this, but we will move some mass flow to here. Let me draw how this look like. Let's bring the drawing here. I don't know, you can see it clearly. So what it's telling us is that we take, you look, this is at 45 bar, and we will take this and mix it here. So we take 15 kilos per second here. Okay, the first thing that you need to say is that it's not possible. We cannot mix steam at 45 bar and mix it with liquid water at 180 bar. We need to pump it, so that's not possible. So let me draw how this process is going to be in reality. See, so we have the turbine. This is point number 2. In principle, it was going through the boiler. Okay, this is the entrance. We have a mass flow here of mass flow. Okay, this is point number 1. Now we are taking some water, some steam here. We take it out, 15 kilos per second. Now our line below will change a bit. We take this, here we have the condenser. We take water from the condenser, we pump it. We pump it, but not to 180 bars now. We pump to 45 bar. Now we have a big cylinder here. We mix this one, 15 kilos of steam with saturated liquid at 45 bar. We mix that. The temperature will increase. The enthalpy mixture, we can calculate that from here, and here we will extract from the bottom, second pump. So we take liquid again and we pump, and we will make it through the boiler. Now that's our point W, okay, and so that's how this will work. And if this is 15 kilos per second, we know that the mass flow here will be m minus 15. Okay, here we have the total mass flow coming here. The total mass flow, no, sorry, m minus 15 as well, because it's coming from this side. Okay, this will join here, so we have m plus, and this is also m plus. Here we are adding 15 to m minus 15, we get the total. Okay, so I hope this is understood. We move. Let's see the question now. What is the amount of steam produced? And we know that now we have this pass through the boiler and this other pass through the boiler. This will go to the point number 3. Point number 3 and point number 4. Okay, so there is one passing through the boiler and another one passing through the boiler, and so we know that the heat at the boiler, the heat that goes to the steam here, has to be mass flow by the difference of enthalpy from 1 to W, H1 minus HW, plus what's going here. It's not m anymore, is m minus 15. M minus 15 multiplied now by the points number 2 to 3. Now that's the heat provided to the steam at the boiler. Now, but we can do some other calculation from the other side. Let's look at the combustion. We know the electrical power is equal 160 megawatts. Electrical power is the combustion of the coal multiplied by the efficiency of the boiler. Okay, this will be the mass of coal multiplied by the LHV multiplied by the efficiency of the mechanical generator and the efficiency of the cycle. So this one here, this is the heat that goes from the boiler to the steam, our Q here. So I can isolate from here. This is the electrical power divided by the efficiency of the mechanical and the generator. Alright. And the efficiency of the cycle. Okay, so I can use this term. I can calculate the heat here, and I know all the enthalpies, and I only need to get the mass flow. So I can do this calculation. I'm not going to do it just now. Just say the solution should be 143.8 kilos per second. That's the solution in question E. But it's true that it's quite tricky. You have to understand this extraction of steam. You mix it here in order to raise the enthalpy at the entrance of the boiler at the beginning, and this brings you more efficiency to the system. Okay, last questions, F, G, H, and I. Which is asking us to determine the specific consumption of coal and the fuel cost per kilowatt hour. Look, here it's important to notice about the heat rate. Understand well the heat rate. Heat rate is how many kilos, how much energy I need to burn, how much energy I need to combust, make combustion to get 1 kilowatt hour. So I need to burn some kilos of coal with a certain LHV to get 1 kilowatt hour. So that's actually my specific consumption of coal, because this tells me how much kilos of coal I need to burn with this LHV to get 1 kilowatt hour. So that's a solution of the exercise, basically. You can solve it in different manners, but that's the specific mass that you are looking for. So then it turns out to be quite simple. You only need to divide the heat rate, divide the new heat rate divided by LHV. New heat rate was 2250, and the LHV is 3900. So this gives us, let me calculate, 2250 divided by 3900, that's 0.577, and this is in units. Remember, this was kilocalories per kilowatt hour, and this is kilocalories divided by kilo. So the final units here will be kilos of coal divided by kilowatt hour. This is really what we wanted. Okay, so that's a pretty simple way to solve this question number F. Let's move now to question number G. It asks us to, it talks about year 2008, and it says that the plant operated for 2894 hours effective full power hours. Okay, so for that year calculate the total amount of electric energy generated. So this question is rather simple. The energy total generated will be the power, electrical power, multiplied by the load. Okay, this is load, number of hours that was operating at full power. Okay, so this one is as simple as this, and we get 463 multiplied by 10 to 6 kilowatts hour. Okay, question H, reactions. Okay, we know the reaction will be like this. We have carbon, we combine it with O2, and we know the composition of air is when we mix it in the air, there is 1 mole of O2. For each mole of O2 we get 3.76 moles of N2. So this reaction will be pretty simple. We will get 1 CO2 plus 3.76 nitrogen. Okay, and we know that this is 12 kilos per kilomole, but this one, the specific weight will be 44, so 12 of one carbon plus 16 of oxygen and 16 again to oxygen, so this is 44 kilos per kilo mole of CO2. So in 1 kilo, now we need to check the composition that we have here. It says coal composition, 45% is ashes, 5% is moisture, and when we remove these ones without moisture and ashes, without water nor ashes, we get 70% and 5% of carbon and sulfur. So for each kilo we remove the ashes and the moisture, so we get 0.5 kilos, and from that only 70% is carbon, so that brings us to 350 grams per each kilo. So, and for this one, each 12 kilos of carbon will produce 44 kilos. So for each kilo, now we need to multiply by each 12 divided by 44. We get 44 kilos CO2 per each 12 kilos of carbon. So we need to multiply these 350 grams by this factor to get the kilos of CO2. That's 1.283 1283 grams that of CO2 per each kilo that we burn. No, okay, but it asks us for the specific. They want kilos or grams per each kilowatt hour produced. From the previous exercise, where it is, previous exercise, we have calculated the specific mass. Where was that? Yeah, here. Okay, we know that for each kilo, okay, now we have this value 1.283 kilos of CO2 per 1 kilo of coal, and we know that for that 0.577 kilos of coal are worth 1 kilowatt hour. Okay, from here we know that this amount we need to burn this coal to get 1 kilowatt hour. So from here we can calculate. We have the this value 1.283 multiplied 0.577, and we get the kilos 0.774 kilos per kilowatt hour emission CO2. Okay, and the total emissions, we will need to multiply this value multiplied by the total amount of kilowatt hours that we produced. So multiplied by 463 multiplied 1 million. Okay, this is the total amount of kilos, so total 3.42 10 to 8 kilos of CO2. You can see the total amount of emissions is huge. Okay, now for question E we do the same. Now I'll do it here small, I think it fits. Now the reaction is very similar because we have S plus O2, so this will bring us SO2. The weights here, this is 32, and this one will be therefore 32 plus 16 plus 16 is 64. And from 1 kilo now we only have 25 grams. So from 1 kilo, let me do it slowly, 0.5 kilos, and then here only 5%. So this is 0.20, so this is 25 grams. And now we need to do the same. We multiply by 0.577 this value to obtain the specific emissions, and also by this ratio 64 divided by 32. Okay, and this brings us the result, which is do it here again, the specific emissions 25 per 64 divided 32 per 0.577. That's yeah, 0.02885 kilos per kilos of SO2 per kilowatt hour. Okay, I think that with this we reach at the end of the exercise. You could also calculate the total emissions. You just need to multiply this value by the value here, this value. Okay, and you will get the total emissions of SO2. I hope this solution helped you to understand the exercise. Thank you for your attention.